Hello. Good evening, everyone. Am I audible to you? Am I audible, everyone? Please confirm in chat box quickly so that we can begin our session for the day. CSIR NET LS June 2021 question paper discussion. Both shifts, shift 1, shift 2, morning, evening. Today we will talk about unit 1. Okay, excellent. Yes, welcome all of you to this question answer session. We'll learn a lot. We'll understand what mistakes we have made and where we could have made a better choice with our questions. Let's begin. The first question on your screen. Following statements are made about competitive inhibition of the enzyme. Uncompetitive inhibitor. They have asked about uncompetitive inhibitor, whether it binds to both free enzyme and as well enzyme substrate complex. Second, addition of uncompetitive inhibitor lowers the Vmax. On the other hand, Km, they have said apparent Km is lowered or apparent Km remains unchanged. So, which of the following options is the correct combination of questions? B and C, A and C, A and B, and A and D. So, whoever answered this question, can you comment on what answer you have selected? Now, studying enzymes, it requires a lot of concepts, especially the inhibition. You should know why an inhibition is happening, what are the sites that the inhibitor will go and bind, whether they will bind along with the substrate or just the alone the inhibitor will go and bind, how will it affect the Vmax, Km, the kinetic properties. Then only you will be able to solve this question. Well, let's look at the answer. Yes, the correct answer is option 1. Now, talking about uncompetitive inhibitors, we know that competitive inhibitors, they bind to the substrate and the inhibitor binds to the same site. But uncompetitive inhibitor, that's not the case. As you can see, this is the inhibitor. Now, the inhibitor directly cannot go and bind to the enzyme. No. First, the substrate has to go and bind to the enzyme, thus forming an enzyme substrate complex. Then only it will open up a space for inhibitor. Earlier, which was not accessible, or the conformation was not like that, then only the inhibitor can go and bind. As a result, the substrate binding will be affected. Generally, this is for multi-substrate molecules. You will think that, okay, substrate has bound, then product will be there. But this is for multi-substrate. So that's why in this case, the velocity will be decreased because enzyme will not be able to work at its full capacity if inhibitor is bonded. Okay. And since Km is the substrate concentration required to achieve Vmax, even the Km will be decreased. So that's why when in the previous, so this is the correct option. Okay. But apparent Km of the enzyme remains unchanged. No, it is lowered. And as I already also told you, the Vmax also is lowered. So you already have your answer, that is B and C. Yes, Vijay, that's right. Your answer is correct. And substrate binding could cause, and yes, in the first question, first statement, it says that it binds to both free enzyme as well as enzyme substrate. No, it does not bind to free enzyme. So this is where it is wrong, the first statement. Okay. So both Km and Vmax are altered, but a distinctive kinetic pattern emerges under steady state conditions. Right. Moving on to the next question. Following are the pKs. This is also a part B question from shift 1. These are the pK values of ionizable groups given in lysine, where you have pK1, pK2, pK3. Now, lysine, we know it is a basic amino acid. So, out of that, you can easily figure out, and lysine has an epsilon amino group in the side chain. So, you can easily figure out what will be the pKr for this. Definitely, amino group will have a basic pK value. That is why we can say that, okay, 10.4. This is for, anyways, they have mentioned it also. And this is for the alpha amino group, and this is for alpha carboxylic group. In case it was not mentioned, I just give you the logic. So how to calculate the pi of lysine? They have asked to calculate the pi of lysine. Now we know for basic amino acids, there is a particular formula, right? It is where you have to see pi means isoelectric point. where the net charge of the amino acid or the protein, it becomes 0. You have to find out at that particular point what are the pK values which are present before and after it, right? So before, at in lysine, if you consider the titration curve, yes, the answer key is 4. Very good, Vijay, your answer is right. So this is the lysine titration curve. As you can see, this is the fully protonated form where uh, all the functional groups are already protonated. Then after the passing of pK1 value, the carboxyl group gets deprotonated. The rest all remains protonated. Then after that will come your pK value 2, which is for the alpha amino group. So now this becomes deprotonated. This is already deprotonated. This remains protonated still. Then last will be the pKr value. So pKr value is 10.54. After that, even your epsilon amino group will be deprotonated. So now everything is deprotonated. Now how to calculate the pi? As I mentioned, you have to see where the net charge is 0. So if you consider all these 4 forms, this form has a total charge of +1. This one has a total charge +2. This one has a total charge of +1. How +2? This is +1, this is +1, this is 0. Like that, +2. This is +1. This form, totally lysine, it has 0 charge. So this is the one with the net charge. And that's why to calculate this point, you have to take the pK points of this one and this one. So that was your pK2 and pKr, right? So for basic amino acids such as lysine, isoelectric pointer pi is calculated by an average of the pK2, that is alpha amino group, and epsilon amino group. So since here these 2 points are what they have already mentioned, you have to just pick them up carefully. That's all. So 9.06 you will pick up and 10.54 you will pick up. Taking those two, you will get an average of 9.8, and that is the correct answer. Yes, come on students, are you participating or not in the question answer session? So how many of you got it correct? Tell me. Anyone attempted, got it correct? Okay, next question. Again, it's a part B, question 23. The enzyme alkaline phosphatase. Okay, a numerical question from enzyme kinetics. It was tested for its catalytic activity using the substrate paranitrophenyl phosphate. Basically, nothing, this information is not required. All you have to know is what was the Km and what was the Vmax. So Km is given in 10 millimolar, whereas Vmax is given in 100 micromolar. So unit conversion will be required. And what have they asked you to find out? Which of the following represents the initial velocity? Initial velocity means V0. They have asked to find out V0, what, where? At substrate 10 millimolar. Everything they have given. So all you have to apply is Michaelis Menten equation. As simple as that. Cannot get more simpler than this. Okay. Just that you have to convert the units. So Vmax, you can keep it in, and yes, we need to see what unit they have asked the answer in. So they have given in micromole. So what you can do is you can keep the Vmax in micromole. Millimolars you can convert into micromole. So to go to milli to micromole, you have to multiply with 10 to the power 3, right? And even the substrate concentration you have to convert into micromole, right? And then you have to calculate the V0. So this is your explanation. Yes, option 1 will be the right answer. Given Km is 10 millimolar. So converting into micromolar, it will be 10 into 10 to the power 3. Vmax will be 100 micromolar per minute. It's already given. Substrate, it's given in 10 millimolar. Again, milli to micro, you have to multiply by 10 into 10 to the power 3. Keep the 10, okay? Don't remove the 10. Sometimes we do that. Converting the unit, we will remove the actual value. Now you have to apply the Michaelis-Menten equation, which I mentioned, where V0 is equal to initial velocity of reaction. Vmax is maximum rate. Substrate, concentration of substrate is S, Km is Michaelis constant. So just substitute all those values, put all the powers properly. So this will be your Vmax, this is your Km, this is your substrate, this is your Km, and again this is your substrate. Don't forget there is a plus in the denominator, okay? You have to be very careful of this, and there is a multiplication in the numerator. So if you do it correctly, yes, it will be 100 into 10 to the power 4, and here you have the 2 into 10 to the power 4, because 10 plus 10 will be 20, and just 20 I have removed to 2 into 10 to the power 4. So 10 to the power 4 gets cancelled. 100 by 2 is 50 micromolar. Calculations are also simple. Okay. Question number 24. How many hydrogen bonds involving the backbone CO and NH? Obviously, backbone in a peptide. They are talking the peptide about the peptide backbone. So this was again a conceptual question. The previous ones were easy, just apply the formula, but this was a conceptual question, right? I hope I'm audible to all of you. Are you guys there? Are you understanding? Did you attend any of these questions, the ones which I'm discussing? Or you all are from shift 2? Please comment in the chat box. Yes. Radhika, Sangeeta, Monica, Amit, Vijay, are you all there? I just want to confirm that I'm audible. Okay, fine, Devanshi. Very good. So, how many hydrogen bonds involving the backbone CO and NH can be observed in an alpha helix, which consists of 15 amino acid residues? Right now, how to solve this question? They have asked, they have given the number. Let me tell you. You are from shift 1. Okay, Vijay. So these are the questions which your paper had, right? Now, see, in an alpha helix, first you should know what is the bonding type. This, many of you who have had a decent preparation would already know that the CO of ith amino acid in a peptide, obviously in a peptide you will have some amino acids, right? So instead of writing them 1, 2, 3, 4, we will just give them, okay, ith amino acid. So what will be the next one? It will become I plus 1. Next one will become I plus 2. Like that, I plus 3. So like this, the bonding in an alpha helix, if you have to form an alpha helix, then the bonding is formed. It's a particular pattern where the CO group of ith residue. So our amino acids will have CO group, NH group after forming the peptide bond. So that interacts with the NH group of the I plus 4th residue, something like this. Okay. So as you can see, this is residue 1. This is your peptide bond. I hope you can understand. There is a C alpha and then again a C alpha. Then again a peptide bond. Then again a C alpha. Again peptide bond. This is your peptide backbone. Okay. And here you have, yes, very good, Vijay. So I to I plus 4, you should also know what group. CO of I to NH of I plus 4. Right. So as you can see here, this is the CO group of the first residue. And which is the I plus 4th residue? This is the I plus 4th residue. Now always peptides we write from N to C terminal. Okay. So that means in I plus 4th residue, that is in this amino acid, this is your NH group of I plus 4 and this is your CO group of I plus 4. Okay. So this group is what is the bonding going to be. This bonding is going to be with this bonding. Okay. So like this, they are going to be connected. Now, what is the next bond? So you just keep on adding. Now, next one will be I plus 1 to I plus 5. There is a regular pattern. So now you can see this is the I plus 1 group. The CO group is right here. And the I plus 5th group, the NH group is here. So this is the bonding which you are getting. Okay. Now they have asked for a 15 amino acids residue which is forming an alpha helix. So there we will consider out of the 15 residues, 1, 2, 3, 4 like this, we will consider the first residue as ith residue and the 15th residue, what it will be? I plus 14th residue, isn't it? 15th residue is nothing but I plus 14 because first one you have considered as I. So then let's see how the hydrogen bonding is formed over here. Here I have taken here till 15th residue, that is till I plus 14th, right? So just let's keep on forming the bonding. I told you what is the bonding that we have, ith residue to I plus 4th. So CO of ith residue, this is I plus 4 and this is the NH group of I plus 4. So this is your first bonding. Okay. Next bonding will be CO of I plus 1 to NH of I plus 5. CO of I plus 1 to NH of I plus 5. This is the, actually it goes this way because donor is NH group. So I will write it this way. So just keep on doing that. Okay. So this group to this group. Then this group to this group. So like this, you just have to keep on making the bonds. Okay. So if you just keep on doing that and keep on counting, then that's what you will get. I hope you got the concept. You have to leave that pattern. See, for example, this is the NH group of I plus 10. So NH group of I plus 10 will join with what? It will join with the CO of I plus, sorry, NH of I plus 10. It will join with CO of I plus 6. So where is I plus 6? This is I plus 6. It will join with this group. Okay, so it will join with this group. So just keep on doing that. and at the end you will get total of 11 total bonds you will get. Now the last one, okay, last four, for example, let's take the CO of I plus 11. So CO of I plus 11 is this one. So if this has to bond with a NH, what group is required over here? You require N plus 15th residue, but you don't have that because it is a 15 amino acid peptide. So that's why this cannot form bond. This also cannot form bond. This also won't form bond. Okay. Similarly, our first bond NH will be from here, right? But these NH cannot form bond. This also cannot form. This also cannot form because they need some amino acids before them, four amino acids before them, which they don't have. So remember, the first four NH group and the last four CO group are not involved in hydrogen bond, as enough residues are not there. So there it was a tricky question. Okay, so somebody would have even started the hydrogen bonding from here. So it's only till how much ever NH groups you had. I hope you got that question. Yes, Amit, did you answer that question? Did you get it correct? So there was one more question in part B in shift 1 regarding iron sulfur clusters, which is the FES. They are the key prosthetic groups that carry electrons in all of the below except which one, right? So this was okay, very good. That's good to know. And you have NADH coenzyme Q reductase, succinate coenzyme Q reductase, cytochrome C, and also the QH2 cytochrome C reductase. So out of this, which one the iron sulfur clusters is not present? They have asked that all of them they will carry, but which does not carry. So this also required a theoretical information, right? So if you see cytochrome C oxidase or the complex 4, yes, that's the answer. Option 3 is the answer. It is a protein containing cofactors. So there are some electron carriers, right? And you should know which electron carriers are there. So heme is there, copper ions is there. It is actually consisting of a multi-subunit assembly of 13 separate polypeptide chains and their associated prosthetic groups. So this is the only option which does not have iron sulfur clusters, okay, which help in the single electron transfers. That's right, Durga Devi, very good. That answer is correct. Okay, it's option 3. And complex 1 contains FES along with FMN groups. Complex 2 also it contains FES along with coenzyme Q. FAD, it's the one of TCA cycle, succinate dehydrogenase. Then cytochrome C oxidoreductase complex 3. So that also contains heme and FES. So complex 4 is the only one which does not contain iron sulfur centers, hence the option 3. Then there was one more question which was in conjunction with unit 13 under shift 1, right? So this question actually it gave a lot of information about biuret. Like a protein solution was taken. You have taken some zero point 0.2 of protein sample, unknown concentration, and you have diluted it with 0.8 water you have taken. Okay. Now this what you have got, this concentration, from here you took 0.5. That means you took diluted solution 0.5 ml. Okay. And to that you added biuret ml, biuret reagent you added. So we know that it detects the protein concentration. If it is there, then the color, purple color will develop from a blue color solution. So the more the purple color, more is the concentration. But that principle is not at all required here. They have directly given that particular sample, you got something, right? You got some color. And what was the absorbance which was taken in a test tube of 1 centimeter? All that thing is there. So that they're given 0.20. Again, this information is not of importance because what are they asking over here? What is the protein concentration? Now, people will think that, okay, you have to apply formula and all that thing in undiluted, but actually it is not required over here. They are simply asking the undiluted solution. They told, no, they have taken 0.2 ml of the protein sample. So how much concentration was there? They are not asking for diluted one because diluted one they have already given the concentration. Why do you need to apply formula? That Beer-Lambert's law, A is equal to ECL, what we will apply it for to find the concentration? Concentration they've already given. Then why, what will you calculate, right? It's a simple trick. So what you have to do over here is you have to find out, yes, the answer is explanation, answer key is 1. So concentration of undiluted protein sample is how much? C1 we will take right? The one which we took, the 0.2 what we took, no, let's consider it as concentration 1. Volume of that undiluted solution, how much you took that volume? 0.2, right? What was the concentration of the diluted solution? So they had already given, no, 4 mg per ml, that from the diluted sample you took 0.5. So what was the concentration? They already mentioned 0.4 mg per ml, right? And what is the volume of diluted solution? So this entire diluted solution concentration they have given, but what was the total volume? So initially you had taken 0.2 of concentrated protein and 0.8 water. So 0.2 plus 0.8 is 1 ml, and that will become your V2. So simple logic you have to apply. C1 V1 is equal to C2 V2, right? So C1 you just put in the value, substitute the values, your C1 will be 20 mg per ml, right? And concentration C, you might think that, okay, here you have taken zero point 0.2 and zero point 0.8, totally 1 ml. So here you have some concentration of the protein, right? Whatever concentration, and that they have set 4 mg per ml. Now from that you've taken zero point 0.5. So doesn't matter how much you take, concentration remains the same. How much volume you take, it's not necessary over here, right? Now, Priyanka asked what would be expected cutoff mark for shift 1. So, we are guessing at Biotecnika with the consent of all teachers, what we have come to a conclusion, it will be a little bit on the higher side. Okay, so you can expect it more than 55, some 55.7 or 6, like that you can expect. Okay, and in percentile, if you are some 98.9 towards the higher percentile range, the cutoff will be there. Let's see. Okay, you can never tell. So I just wanted to give you a heads up. Tomorrow we are starting with our Shaurya batch for Net Life Sciences. If anyone is preparing for June 2022, then this is your chance, because this is a very good opportunity as you're getting a free pen drive. Okay, video pen drive you're getting of all the units, the important topics, I mean all the topic classes you will be getting, and plus you are attending live classes, online interactive sessions, you're attending the raid classes what we have, and doubt solving is there 24/7. You're also getting a printout of the hard copy study material and video backup of all classes in that pen drive. So it starts tomorrow. You have to work hard, faster if you want to enroll. You can contact us, our toll free number or our branch number. If you want, you can do that. Amala Deepa, for shift 2, we are also estimating that it will be little bit on the lower side, not as high as shift 1. Okay, so what we have understood is that shift 1 cutoff may be higher than shift 2, because the question pattern and the topic of questions were very restrictive. But in shift 2, the options were more. So even if you had not studied all the topics, you can still do that. Okay, our admissions are closing soon, so you need to hurry up on this Shaurya batch if you want to become a part of it and want to success in CSIR NET. Okay. Next, now these are your part shift 2 questions. Okay, part B shift 2 questions. Let's talk about them. Yes, this was from metabolism. In shift 1, there was no metabolism question, but part 1 did see metabolism questions. Phosphofructokinase catalyzes one of the regulatory steps in glycolysis. So, which one out of these metabolic changes lead to the activation of phosphofructokinase? Yes, so increased ATP concentration, decreased AMP, high citrate levels, and increased fructose 2,6 bisphosphate concentration. So where do you see this? Phosphofructokinase, PFK1 is an enzyme that you see in glycolysis, in the third step of glycolysis. So glycolysis converts to glucose converts to glucose 6 phosphate, glucose 6 phosphate to fructose 6 phosphate. So that is where you need that enzyme. Okay, rather the second step I should so fructose 6 phosphate is converted to fructose 1,6 bisphosphate. So that is where you need the PFK1. So that is the third step you need that. Okay, PFK1. Now how is this controlled, how is this regulated? You should know this PFK1, right? Now see, one of the option is says 2,6 bisphosphate. So don't get confused by 1,6 bisphosphate, because that's a product, but 2,6 bisphosphate is from a separate pathway. Okay, so yes, the answer is option 4. Option D is only the first choice, right? So what is the explanation over here? If you see, PFK controls the entry of the glucose 6 phosphate into glycolysis. Now when the rate of PFK is slowed, if you don't want glycolysis, then PFK1 will be slowed down. You want this enzyme to be inhibited. So then G6P will get accumulated. G6 glucose 6 phosphate won't be getting forward in the glycolysis, right? So in that case, it will be shifted towards the glycogen synthesis. That is the glycogen synthesis to store the glucose. So this happens when the excess glucose will be present, right? PFK is allosterically regulated by several factors. So one factor is fructose 2,6 bisphosphate, which positively activates this phosphofructokinase. Right? I told you that this fructose 6 phosphate to fructose 1,6 bisphosphate (PFK). Actually, this comes from fructose 6 phosphate only. Fructose 2,6 bisphosphate comes from fructose 6 phosphate only when the concentration is high. So then only you will get this, right? So this effector is allosterically stimulating PFK1. That's why D is correct. And the question they have asked is which out of this will be the lead to the activation. That this activation inhibition questions you have to be very careful. They're asking for activation, right? So here the fructose 2,6 bisphosphate is stimulating. But if you see AMP, they ask that decreased AMP, what they will do. So increased AMP, it will activate phosphofructokinase. But they asked decreasing AMP, what it will do. So decreasing AMP will not stimulate. Decreasing AMP will not be able to stimulate because higher AMP will be able to stimulate. So that is also why this decreased AMP concentration cannot stimulate. So it is wrong. B is wrong. And ATP and citrate, they are negative effectors. Okay. Because think about if too much ATP is there. ATP is a energy currency. If too much of energy is there, then what will happen? The cell will not require to make any more energy. Glycolysis is energy producing pathway, right? So that's why too much ATP and citrate, which is the starting of the TCA cycle, if these are too much, then also glycolysis will be getting stopped or it will slow down. So these are negative effectors. That means if their concentration is high, PFK will get inhibited. See, minus sign you are following, no? That means if their concentration is high, then this enzyme gets inhibited. But in the first and second option, third option, what they have said, increased ATP, high citrate. So increased ATP and high citrate is going to inhibit the enzyme, but question is asking activation. So that's why this is also not correct. None of this is correct. This is the correct answer. How many of you got it correct? Tell me. Did you attend this question? How many of you got it correct? So before I move into the next question. What is the net charge of the peptide? Tyrosine, valine, arginine at pH 5. Yes. Again, a PI calculation, a net charge calculation question. So this was there in shift 1 also. In shift 2 also, it has come in part B. Now they have given some PK values. PK values of alpha amino group is 9.6. PK value of carboxyl group is 2.3, and pK of tyrosine and arginine side chain, because see valine is non-ionizable side chain. Okay, not you're not opted for that question. Okay, no problem. So pK of tyrosine and arginine are 10.46 and 12.48 respectively. So which out of this will be the net charge? Yes. No, no, no. Botany of desire, no. It's not increased ATP concentration, because increased ATP concentration will lead to inactivation of PFK, inhibition of PFK. But question asked what will lead to activation of PFK. I hope you got the answer, right? Yes, we have to calculate the net charge. So for net charge, what do you have to do? Let me explain to you. Yes, the correct answer is option 1. See, for the mentioned tripeptide, they have already told which are the groups to be considered for ionization. So these are all ionizable group: tyrosine side chain, arginine side chain, alpha carboxylic group, right? And alpha amino group also. Alpha amino group is also there. So that pK value is 9.6, not mentioned. So valine is not ionizable. So we will not consider it for charge calculation. Okay. So we need to know a logic that when the pH is less than pK point. What is a pK point? pK point is the point where a group will dissociate or it will lose a proton. For example, if you have your carboxylic group, okay, whose pK is given 2.3. So at 2.3, it will become deprotonated. So you can see its proton will get dissociated. Okay, so that is what is the pK point at which it will get dissociated. Similarly, NH3 plus group, it will dissociate into NH2 plus H plus. Again, it will happen at the pK value, which is 9.6. Only at 9.6 this will happen. Okay. Tyrosine arginine also has similar amino group, but tyrosine has OH plus, but this will happen at the pK value what they have given 10.46, right? But you need to know a logic that if the pH is less than pK point, so this is the pK point where it will get dissociated. But if pH is before that, the group is still protonated. It hasn't dissociated. But if the pH is above that, then the group has deprotonated. Got it? If the pH is more than that, right? Okay, so Roblox, you can do one thing. You can go to the settings. If you just click on the video once, there will be a wheel setting over there at the corner. You click on that, and there you will have quality. The quality you can change whatever you want, the resolution 720p or 1080p, whatever you want. So then it will become clear. Okay, just try it out. Yes, so what I was saying is below the pK point, the group will be protonated. Above the pK point, the group will be deprotonated. Yes, Aman Jha, you can just try that. Okay, click on that nut point of thing which is there, and if you click that, you will get the resolution. So pH is less than pK point, the group is protonated. pH is above the pK point, the group will be deprotonated. Now we will consider each of these groups and see what will be the protonation and deprotonation, right? So I consider all these groups. So let's check amino group. Amino group's pK point is 9.6 and they have taken pH 5. At pH 5, what will be the charge? So pH 5 is less than 9.6. So group will be protonated and will exist as NH3 plus. So what is the charge on this? Plus 1. That's right, setting button. Correct, Amit. Right? Then next will be tyrosine side chain. So this is, you can see you have got plus 1 over here. Tyrosine, that is OH group. What is the pK point? 10.6, 10.46. And what is the pH they have asked for? pH 5. Again, it is less than the pK point. So what will be the form of it? Again, protonated. So it will exist in the form OH only, for whom the charge will be 0. Then you will have arginine side chain, which is having NH2 plus. The pK point is 12.48. There also the pH 5 is less than the pK point. So again the group will be protonated. So what will be the charge on it? Plus 1. See, whenever we write anything in the superscript, no, like this, that is what is the, we have to consider the charge. Okay. If we write OH, nothing is written over here. That means the charge is 0. That is why OH will have charge 0. Fine. Alpha carboxyl group, it will be CO minus. So since the pK value is 2.3 and we are taking pH 5. So what will happen? The pH is more than the pK point. So group will be deprotonated. Carboxyl group will be deprotonated and it will have a charge of minus 1, because the deprotonated carboxyl group is in the form of COO minus, right? So total charges if you take plus 1, 0, plus 1 and minus 1, total charge you will get plus 1. So that's why the answer is plus 1, option 1. Okay. Next question. Again, shift to another question was there. So this was a very common question. I think it had come before also, right? Protein X is an all helical protein with 100 amino acids, including 2 cysteines and a pi of 7. Actually, it is not required. This is irrelevant information. Okay. Which one of the following graph best describes the solubility of the protein under, like, I won't say irrelevant, but yes, like in you don't have to go to so much details to solve this question, because this ammonium sulfate behavior is applicable to proteins in general, right? Which of the following graphs best describes the solubility of protein? So generally you understand that this salt, ammonium sulfate, if you keep on adding, then the protein undergoes some changes. So various graphs are given. You have to know to how to analyze a graph. If salt is increasing, in first graph it is showing that solubility is increased. With less salt concentration, solubility is high. Then as you are proceeding forward, the solubility is decreasing. Or initially the solubility is less, but as you increase the salt, it increases till a certain point. After that, more salt, the solubility decreases. Solubility remains same no matter how much salt you add. and solubility increases with salt concentration. So which out of this will be the correct choice? Option 1, option 2, option 3, option 4, right? So I hope you all are aware of the salting in and salting out option. So yes, our answer key is option 2. In bulk protein purification, common step is to precipitate your proteins. You want to take out your protein. You don't want the other junks things of the cell, right? So to purify your protein, you need a salt such as ammonium sulfate. This process is called as salting in and salting out. There's a lot of reasons why you use ammonium sulfate only, and this is performed by adding increasing amounts of ammonium sulfate and collecting fractions of precipitate protein. Now see over here, initially what you take, when you take proteins will have some hydrophobic interaction regions. They will interact with each other with electrostatic interactions, right? So when you add, you don't have salt molecules, then the protein is not interacting with salt, it is interacting with nearby water. Okay. Now what happens, you include salt, but salt is not enough. So what is happening, you can see the protein is interacting with each other, right? But again, individual proteins are also there in water. So solubility increases. During the salting in process, salt molecules increase the solubility. You see, it reaches a certain point where the hydrophobic groups are separated. Instead of interacting with each other, now the hydrophobic regions and the protein parts, they are interacting with the salt instead of interacting with each other. So basically, the protein's electrostatic interactions are reduced when you start adding little bit of salt concentration. Okay, that is what is called as salting in. That is initially increasing the solubility in the graph. Then later what happens, as the salt concentration is increased. Yes, Harsh Shah, good evening. We are solving CSI NET question paper over here. Both shifts, that is June 2021. Topic is Unit 1. All biochemistry questions we are discussing. Okay. So as the salt concentration is increased, the hydrophobic groups on the proteins get exposed to the atmosphere, right? Attract other protein hydrophobic groups because now so much of salt is there. So what will the salts do? They will aggregate with each other, right? And they're interacting with water. So what is happening to the protein? The protein hydrophobic groups are again exposed and they will join with each other. They will aggregate with each other. So protein-protein interactions become more energetically favorable when you increase the salt concentration beyond a certain point. And if that happens, then proteins aggregation means what? They will precipitate out. They will become insoluble from the solution because all the salts are interacting with the solution. That is the water. So water is not interacting with the protein. And that is why proteins precipitate from solution. So solubility will decrease after a time. So initially it increases, that is salting in, and later it is salting out when it decreases. So answer is option 2, which shows a bell-shaped curve like this. Okay. Next question. This was a very easy question again in part B shift 2. So 4 sequences are given. Okay. So Harsh Shah, what you can do is you can go on the setting button. In YouTube, you will find that wheel at the corner. From that setting button, you can select the resolution as 720p or 1080p. Then the screen will become clear. Okay. Just try it out. Now these are all the sequences that we have. The sequences, they have given some few sequences. Out of these sequences, you have to place in order. Order of what? You have to put the order of melting temperature. Okay, they have asked to put the TM actually. What will be the TM for all of them? And first you have to find out what will be the TM and then you have to put it in the order, right? So all you have to know is a knowledge that in DNA Watson-Crick bonding, the G's are triple bonded with C and the A's are double bonded with T. So triple bond means what? It will require more energy. TM is basically the melting temperature. Melting temperature doesn't actually mean like ice melting into water completely, structure is changed, not like that. So if you have a DNA, then if it separates out into single strands, that is where it gets denatured. That is the point where we will understand half of the DNA, how much temperature is required to melt that. That is what is TM. So obviously, if you have more bonds, hydrogen bonds between the two strands, you will require more temperature to separate the two strands. So simple logic, more the GC content, more TM will be required. Lower the more the AT content, lower will be the temperature. Okay, so that's a simple logic All you have to do is you have to just count how many GCs are there. Okay, 1 GC, 2 GC, 3 GC, like that you have to count. 4, 5, and 6. So that means sequence A has total of 6 GC bonds. Like that you have to count. Okay. Nitrogenous bases are purines and pyrimidines. The pyrimidines are thymine and cytosine. Purines pair with pyrimidines. So all of we know that the adenine pairs with thymine by 2 hydrogen bond, while the cytosine pairs with guanine by 3. Right? So the one with higher GC content will have higher melting temperature. What is TM? It is the temperature at which 50% of that DNA will become separated into single strands. Okay. So in DNA fragments, A sequence has 6 GC pair, B has 14, C has 10, and D has 12. So the sequence will be B first, then D, then C, and then A. So option 1 is the right answer. I hope you followed. So there was another TM based questions in the shift 2, but actually it was dropped because they were supposed to give a TM profile, the melting temperature, DNA melting profile, a graph they were supposed to give. The question mentioned that in the graph, but actually there was no graph in the question paper. So that is why it was dropped. So I think they replaced with some another question or something, right? So those were all your part B questions. I just want you to remember that yes, this if any of these questions you feel that it's not solvable by you or you're not understanding, as I already mentioned, you can take help. Biotecnika is there with Shaurya batch. You can enroll in it and you can prepare for June so that you can clear it and pursue your dream research. So miracles will start to happen when you give as much as energy to your dreams as you do to your fears. Don't be scared of this exam. Everyone prepares, and with proper help and guidance, they will definitely clear the exam. Okay. So let's start off with our part C question. This is from shift 1. The first part C question: a schematic of the metabolic pathway is shown below. So this is what is the schematic they have given. Yes, there is a some D molecule, it's converted to E, it's converted into F. F is going to G and H. That means F is the precursor for both G and H. That is separate pathways. Okay. G is going to K and then H is going to L. Right. So, how to improve in biochemistry papers, Amit? How to perform better in biochemistry questions? The only thing what you require is concept, right? Concept is what? Knowledge which you can apply in different questions. That is what is concept. So, understanding first is the key from the books, reference books, but reference book takes a lot of time to read. So, if you have limited time, that's where you can take help from Biotecnika. You can attend the classes where teachers will explain what is written in the books in a shorter period of time, a concise manner, and most important concept they will make you understand. And they also make you practice questions in the class which you will understand the application for, so that how to apply the questions, how to apply the knowledge in questions, you will get that approach. Okay. DBT GRF application form, it will be notified. Don't worry. Seema, you can subscribe to Biotecnika newsletter. Go to our website. There, Biotecnika newsletter. You just subscribe. So every day you will get the mail. Okay, in your official mail ID. So there you will get all the informations. Don't worry. Okay. So which of the following conditions would stoichiometric amounts of end product K and L be obtained in a concerted feedback if a concerted feedback was in operation? Simple logic, they are saying if this pathway follows concerted feedback, then what will be the condition of the end products of K and L? Means how these things will be inhibited. That is what they are asking. Okay. So one, and they have said that K inhibits the conversion of F to G. That means there is an enzyme over here, right, which is converting F to G. There is an enzyme over here. So K inhibits that enzyme. That is one. Okay. And L inhibits F. So L inhibits F to H. So you can see F to H, L inhibits F to H. Right. Then D to E, that is D to E, is inhibited by equal amounts of K and L. So K and L goes and inhibits D and E, D to E equally. That is one option. Then like that they have given some options. D to E is inhibited at equal amounts of KL, same concept. K inhibits F to H. Now how is that possible? This enzyme, we know feedback inhibition will be upon its own synthesis. So how can this go and inhibit this one? That's not possible. So this option will not work. Okay. D is inhibited at equal amounts, and K inhibits F2H. Again, K inhibits F2H. Again, this option is not applicable. And this inhibits F2H and L inhibits F2G. So let's see what is actually concerted feedback. Yes, the answer 1 is only the option. Explanation: according to the representation of certain feedback reactions, which I'll tell you, in concerted feedback, what happens? The end products. So here you can see a similar pathway is given. So this is the end product X and Y, which will go and inhibit their own synthesis. So as you can see, this is preventing its own synthesis. So this sign stands for inhibition. Similarly, this is inhibiting its own synthesis. Okay, by blocking their respective enzymes. So that's why the options where they are blocking the other pathway enzyme, that is not correct. They will only block their respective enzymes, and also more than one end product or all end products must be present in excess. So both X and Y will be required, then only, and that too in excess is required, then only they will go and inhibit its own synthesis. Okay, like not both should be present, but yes, one or another or all the end products must be present in excess. That excess is important to replace the first enzyme. That's why the option 1 is correct. Okay, so I was saying, no, there are many such feedback pathways. So these are the things. If you are in class or something, you don't know what to learn. Now if you study based on previous questions, you'll probably only check what is concerted, but in classes you're getting to know what will be cumulative, divalent, isofunctional, sequential, so that you have a detailed information. It's just that classes help you in detailed preparation in a short phase of time, which is appropriate for, and not only that, for application in the questions also. So that is apt for clearing CSIR exam. Question 72, that is part C, the second question. Following statements are made to define Michaelis constant. So everyone studies enzyme kinetics, they know what is Km. But do we know these things? Let's check. Whether it's an intrinsic property of enzyme or not, Km. And does it depend on pH, temperature, ionic strength? That you have to know. Is it independent of enzyme concentration and substrate concentration? Or is it equal to the dissociation constant when ES complex dissociates more rapidly than product? Or is it equal to dissociation constant when product formation is more rapid? ES complex dissociation is more rapid, or product concentration is formation is more rapid? So which of the following is correct? Yes, again you need a concept over here. So in this question, could I see the question? Yes, yes, sure, Ashwin. So this was the question. Question 71, part C question. This was the one. So you can all join our Telegram group, okay? You can get these questions and the solution also. That question paper with solution, it will be posted over there, right? So link will be given to you later at the end of this class. There you can join the Telegram group. You will get the link to join, okay? Okay, so let's see what is there in question 72 in enzyme Km, related to Km. Now, all of us know that enzyme has its specific Km value that is independent of the concentration of enzyme. If you didn't know that, okay, yes, it doesn't depend on the concentration of enzyme. Yes, it is an intrinsic, it is a property of the enzyme, agreed, because Km value, if you have to define, it is the substrate concentration required to achieve half of Vmax, right? So it is independent of the concentration of enzyme. Now, second statement is based on Briggs-Haldane equation. Second and the third statement, which said that the Km value is equal to Kd in what condition? Whether the ES formation, whether the product formation is more or the ES dissociation is more. So, in which case Km is equal to Kd? That's what they have asked. So, many of us won't know about Briggs-Haldane. That's what I said is it's the advantage of attending classes, right? An alternative to the Michaelis-Menten theory of the kinetics of enzyme. Okay, it is an alternative actually, because Michaelis-Menten, it assumes that ES to E plus P. So this they assume that it is K cat, which is very much slower, and this process is very much fast. That's what it will assume, Michaelis-Menten. Okay, but the Briggs-Haldane will assume that no, the breakdown of enzyme substrate complex, see, breakdown can happen this side also, it can happen this side also. Either it can break down into E plus S individual, or it can convert into product. So Briggs-Haldane proposed that breakdown of a ES complex to product is not slow in comparison with dissociation. No, it is not assumption in Briggs-Haldane. Okay. Now, from the Michaelis-Menten kinetics, we get Km formula as K of. K of is the breakdown of ES. K on is the formation of ES, right? And Kcat actually we give in the form of slowest reaction step that we call as rate limiting step, right? So that's a formula for Km, whereas for Kd it is K off by K on. Okay, so as you can see, basically Kd formula, it is K off and then divided by K on, divided by K on. The only factor which is there is the Kcat value for Km. So clearly Km will always be greater than Kd because it has an additional factor in the numerator, which is Kcat value. Okay, but there is a condition. Michaelis-Menten assumed that substrate binding and dissociation, that is how they are binding and how fast they are dissociation, that will be much more rapid than product formation. Yes, they assume that this is much faster step and this is a slower step. So that is why in that case, Kcat becomes very less. Basically, this is the rate constant. Kcat is the rate constant, which how fast the reaction is taking place. Okay. So if it is a slow reaction, rate constant value will be lesser. So if it is a lesser value, you can almost ignore this, right? So in the equation, you can almost ignore this value. If that is the case, then Km becomes almost equal to Kd. Okay, so what is the condition in which Km will be almost equal to Kd? Where the ES complex dissociates more rapidly than product formation. Yes, it moves this side rather than this side. ES complex comes back to more ES, that tendency is more rather than going to the product formation. So that's why we will call this B as correct statement. And yes, what about the dependency on pH and all? Value of Km is minimum at the optimum pH of an enzyme. It increases with changes in the pH of environment. Okay, so it was saying that it is independent of pH. So that's why these all are wrong. And Michaelis-Menten constant value decreases if the temperature is increased till the optimum temperature. Any further rise in temperature will decrease the enzyme activity. So as you see here also, definitely it is taking the account of temperature and pH. So since this statement is saying it does not depend on pH, this is also wrong, right? So the correct answer is A and B. Option 1 is the right answer. Moving on to the next part C question in shift 1. So here it was a simple question based on the biochemical characteristics of proteins and experimental procedures which are used to determine them. Match the characteristics with the experimental procedure. Very simple. Now all of us know NMR, it is used for characterizing the 3D structure of proteins. Isoelectric focusing, it helps us to detect the ionic charge, the pi of the protein. And affinity chromatography, it is based on the binding specificity, and ultracentrifugation, it separates molecules on molecular size. So it was very simple over here. Yes, D4, C3, and so second is the right option over here. Okay, so let's see what is the explanation. Yes, NMR is used for 3D structure viewing. Basically, this nuclear magnetic resonance, it is used for molecular structure of a material. We are studying that to be analyzed by observing and measuring the interaction of nuclear spins when they are placed in a powerful magnetic field. So for the analysis at the atomic level, these electron microscopes and extra diffraction instruments can be used. And when the nucleus that poses a magnetic moment, okay, such as hydrogen nucleus or carbon nucleus, it is placed in a strong magnetic field, that time it will begin to precess like a spinning top, right? And that's where you can find out a certain spectrum. If the sample is placed in magnetic field and irradiated with radio waves, you can find out the frequency as NMR spectra. So that will help us in viewing the 3D structure, right? Isoelectric focusing can be used to determine the ionic charge of protein. So as you can see over here, there is a cluster of all proteins at different pH, but later they get arranged according to their own pi. What will be the charge? So what's the concept over here? If you take a mixture of proteins, in a particular pH strip, like from 3 to 10 pH strip if you take, according to protein's pi and independent of the size, they will get separated. Okay, so we know that if the pH is equal to pi, then there is no net charge on the protein. So there will be no net movement. So there it will get stopped, right? It is theoretically possible to separate the protein and to determine the pi value of the protein by monitoring these electrophoretic movements. So isoelectric focusing, it can be used for many other purposes, like to examine post-translational modification of protein, or like mass of a protein, in something which you cannot resolve by SDS page. It can be also used for fractionation of protein or peptides prior to mass spec. Right, all these things, again, if you only if you know the things in detail, then only you will be able to answer such questions. Okay. The next is binding specificity of proteins. It is exploited in affinity chromatography. Yes, affinity for a certain molecule. So what we are having over here, you have many different molecules, but you see only the red color molecule is having affinity towards your column, and only those will get bonded. So if those get bonded, only those will get separated, right? Plus, you have in ultracentrifugation, molecules are separated on the basis of their size. So, we understand about the density, what we have in ultracentrifugation. If density is more, then they will get separated at the earliest. So, you can pour off the supernatant, because you can see these are of smaller size, right? The bigger size molecules are getting precipitated, in the pellet you will get. So, again, the supernatant, if you centrifuge, then the next size molecules are getting in the pellet, right? So like that you can separate off your molecules. So that's why the option 2 was the correct answer, right? Next question in part C, shift 1. Yes, it was emission spectra based, UV spectra based. A circular dichroism spectra in the far UV region informs on the kind and content of secondary structure. So what they are saying, the far UV region, it gives you an idea of secondary structures. Near UV and tryptophan emission spectra, that is near UV and tryptophan emission spectra, it gives you a concept for 3D structure. It will tell you about the 3D structure, right? So all you have to do is you have to see the changes, what is happening in these graphs. It's not such a difficult question. So where you can see the changes, what is happening in the native form, obviously, right? And the green graph, what you are seeing, the green graph, what you are seeing, the green graph, you can expect it to be, that is in pH 3, that is the green graph. So some changes you can expect to see in the protein. And pH, this red color graph, that is in the presence of guanidine hydrochloride. So you should know what is guanidine hydrochloride doing. Well, it is a denaturant. And what it will do, it will break the hydrogen bonds, it will disrupt the hydrophobic interactions. So basically, you can expect with 6 molar guanidine hydrochloride treatment, the protein will be denatured. So if protein is denatured, we know the tertiary structure will not be there. So red color line, you can see that if you compare with the black color line, which is native protein, and if you check the red color line, which is denatured protein, you can see in tertiary structure emission spectra and near UVCD, both the graphs are different. Correct? And here also you can see the black emission spectra line, native emission is at a lower range, but the emission at the red color denatured graph, it is showing more. Okay, so what does this experiment report? First is that protein is fully folded at 7 pH. That means the black line is showing that protein is fully folded. When acid induced treatment is there, it leads to the formation of molten globule. That you can figure out from the secondary structure, because molten globule is an intermediate form. So basically you have native protein and the denatured protein. So from denatured it goes to an intermediate form, rather you can say a molten globule form, where only few of the secondary structures are present, but entire tertiary structure is not there. Okay, so if the protein is in molten globule form, your secondary structures may remain intact. There won't be any change in them, which we can clearly see in this graph. See, this green is acid induced line and the black is the native protein. You see that there is not much change in the two graphs. But yes, the red graph is showing a complete change. It is a flat line. Flat line means that the secondary structure is completely disrupted. But here you can see even the acid treated protein, it has some secondary structures which hasn't seen a drastic change in the pattern. So we can conclude that this is in molten globule form. The acid induced one, it has not completely denatured, but it is in the molten globule form. Okay, but yes, somewhat it has disrupted, because that's how in the 3D structure you can see that the 3D structures the change is seen. The green line changes are seen in the 3D structure, but in the secondary structure CD spectra, what it will show, we are not seeing much change, which means the secondary structure is intact but 3D structure is disrupted. So this will be the correct answer. Protein is fully folded at pH 7, acid induced molten globule at pH 3, and unfolded in 6 molar guanidine hydrochloride. Okay. So these are all not correct, because see, if protein structure is reduced at pH 7 and the protein has formed beta fibril at the other two condition, you would have seen some changes here. The green line, you would have seen some changes. Since you don't see any, this won't be the correct answer. The changes in fluorescence and near UV induced spectra, there is some changes in hydrodynamic radius. So I'll be explaining you what is this hydrodynamic radius. Basically, for denatured protein and native protein, the hydrodynamic radius, it will decrease. But since it is saying increase, there this statement is wrong. Okay. And the extensive denaturation of the protein both at pH 3 and in 6 mole guanidine hydrochloride. Extensive denaturation means what? Secondary structures also gone. Secondary structures also disrupted. But clearly that is not the case, because here we can see that there is not much change in the secondary structure. So even this is not the option, right? So option 1 is the right answer. As I already mentioned, compared to the black line, green line shows a change in near UV also and fluorescence also, which indicates there must have been a change in the tertiary structure. On the other hand, in the far UV, it doesn't show much change, indicating that at pH 3, there is no change in secondary structure. So that is why statement 2 was wrong, where it told that it shifted to a beta fibril. So that cannot be applicable. Now this is only possible in molten globule state, where it has maintained its secondary structure, but yes, tertiary structure is somewhat disrupted. Okay, so statement 1 is correct. And red line, if you talk about guanidine hydrochloride, which acts as a denaturing, it increases the emission maxima, which means that yes, slowly green, then red, it is slowly getting denatured. It is exposing its tryptophan. The more it is opened up polypeptide chain, more the tryptophan will be exposed outside because of the denaturing treatment, and that is how we are seeing a loss of the tertiary structure. Okay, in red structure it is completely falling flat, so that is an indication that yes, it has completely denatured. Okay, that is with 6 molar guanidine hydrochloride treatment, the protein is completely denatured. And what is hydrodynamic radius? For native folded protein, it is more, but for denatured protein, the radius will be less. So hence with denaturation, you can expect an increase in the radius. Okay, sorry, with the denaturation, you can expect a decrease in the radius. But since the question says there is an increase in hydrodynamic radius, that is wrong. Okay, so that's why only option correct is option 1, right? I hope you all are following. Yes, you're getting to know where you all have made mistakes, and you can predict whether you will clear this exam or not. But don't worry, if even if you're feeling low, if some question are getting wrong, don't worry, let's hope for the best. But in at the same time, you have to also keep preparing for the next exam. Okay, so do that, and you can take help if you want. Pi of protein, 4 proteins are shown in the table given over here. Yes, you have protein A, B, C, D, and the pi values 4, 5.5, 7, and 9. So you have to purify protein D out of that. Out of all this combination A, B, C, D, all proteins are there, you have to purify protein D, and that too with a single step using ion exchange chromatography. So what combination of buffer pH and ion exchange resin will you select? So you have to have a particular pH and whether cation exchanger or anion exchanger. That is the question. So here also the concept of pi is applicable, that if the pH is less than the pi, then the net solubility charge on the protein, okay, if the pH is less, the net charge will be positive. And if the pH is more than the pi, the net charge will be negative. Okay. So, what is our exchangers? Yes, our exchangers exhibits net negative charge. And if it is negative charge means what? It will bind to positive charge. And if it is negative charge means what? It will bind to opposite charge column, that is positive charge it will bind, right? If pH is equal to pi, then no net charge and no binding. And if pH is equal to pi, then it has a net positive charge and it will bind to cation exchanger, right? Positive charge means what? It will the one which will exchange the positive charges, right? So something like this. You can see the column over here is negative charge, right? Cation exchange means what? The column will be negative charge, and anion exchanger means the column will be positive charge. So what will bind to the positive charge? Negative charges will be binding. Already some negative groups are there, but they will be exchanged for further negative groups which are there in your mixture. Okay, so negative groups will be exchanged with the other negative groups which are already bonded to positive. That is what is anion exchanger. And cation exchanger means the column will be negative. There are some positive groups bonded to the column, but when your mixture sample, if it has a positive charge on it, if any protein has positive charge, they will get exchanged with the other positive residues in the column. Okay, so that's how they will get stuck. As you can see, the green ones, they are getting stuck over here. Later you can remove them and you can purify the green ones, you can remove, but at least your other proteins will get purified from there, right? So obviously what I want over here is, if you look at the pi values, all 4, 5.57, all are below 9. So if you consider the pi value of d, because we have to purify d, if your pi value is 9, okay, no problem, Amit, you can watch the recording later. So if the pi value is 9 and if you take a pH below 9, okay, so what will be the net charge on d? If you take it below 9, the net charge will be positive, right? And for A, B, C, all of them, if you take any pH above them, that is 7, above 7, if you take pH, let's take 8, right? So if at pH 8, all of them, you can see their pi is less than the pH, means the pH is more than their pi. So pH more than their pi means they will carry negative charge. So all of them will carry negative charge. Now, if you take a cation exchanger which has negatively charged column, so D will, you're passing A, B, C, D all from here, but your A, B, C all are carrying negative charge, but your D is carrying positive charge. So that will get stuck. Got it? That will get attached to the column. That's why you can select a pH which is less than D and a pH which is more than ABC, so that ABC can exist in negative charge, whereas D can exist in positive charge. So that's why this will be the answer. At pH 8, you have to select a cation exchanger, because at pH 8 your D will be positively charged. So you need a opposite charge column for that. That will be, and they should exchange cations for it. I hope that is clear to all of you, right? So there are two types exchanges, right? A cation is an ion with positive charge, and a cation resin is one that exchanges positive ions. Got it? So basically, any pH below 9, protein D will carry a net positive charge and will bind to cation exchanger and can be purified. Also at any pH above 7, the other proteins will carry net negative charge, hence will not bind to cation exchanger. The other ones which are negatively charged, they will pass away. That is ABC. Okay. Then another question was there in shift 1, part C question. Now this was in conjunction with unit 7. Okay. So plus there was one more question of hemoglobin and carbon dioxide, that is also from unit 7, that will be discussed in unit 7 discussion question paper. But let me just tell you this because it has concepts of unit 1, right? This curve B, what you can see in the figure, it shows the oxygen dissociation profile. Physiological CaCO2 is also 7. But in physiological CaCO2 is also 7. Okay. Now you should know that the CO2, if it is more, it joins with water and it forms carbonic acid. So carbonic acid means what? Acidic means pH will be less. So remember that if CO2 is more, pH actually decreases. Okay. But anyways, here what they have asked, if there is an increase in pH, they have not asked for CO2, they are asking if there is an increase in pH, then what profile it will lead to. So one option is that it will be B only, no change in the graph, or curve A where it has taken a little bit of left shift, or curve C where it has taken a bit of right shift, or curve D where it has completely fallen flat. Okay. Now you should know that there is a dependency of pH on oxygen binding, which is called as the Bohr effect, right? And it is directly proportional. If pH is increased, the affinity of oxygen binding is increased. If pH is decreased, the affinity is also decreased, right? Now we know one more point, that we have to find Km value, right? Km value we have to find out, or rather Kd value you can say. Wherever is your maximum saturation, see this is saturation, means how much of the protein is binding with the oxygen. This is oxygen concentration, which we take in partial pressure, because we cannot actually measure the concentration of oxygen molecules, no. So partial pressure, here it is 100% bonded, all are bonded, that is why you see no more change in the binding. Okay, no more, even if you increase oxygen concentration, still no binding is taking place. So here it is 100% saturation, all proteins are bonded with oxygen, right? So take 50% of that, and from 50% you can just extrapolate the line and see how much oxygen is required to get that 50% binding. Okay, you have to see how much oxygen is required to get that 50% binding. From here also you just pull it down, from here also you pull it down. Now for all of them you are seeing, in graph A you need least oxygen. In graph A you need least oxygen to get 50% binding. That means what? The affinity in graph A is more. So you should know that the Kd value is inversely proportional to affinity. And these points what you are getting, that is actually affinity, that is actually Kd points. Okay. So if your Kd value is less, which is the case for graph A, your affinity is high. Got it? So they are asking if there is an increase in pH, what is going to happen. So what did I tell you? Increase in pH means you will see affinity increase. So that means what? Affinity, if it is increasing, you can expect a lower Kd value, which is showing in graph A. So curve A is the answer. Did you get it, Vijay? It is not options 3, it is curve A is the answer. Right? So simple logic, dependency or bone on Bohr effect, pH increase, affinity increase, and we know that if affinity is increasing, we require less substrate to achieve saturation. And because of that, the graph takes a left shift. So basically, we can take this reference that there is a certain P50 value. P50 means how much concentration or partial pressure you require to get 50% of binding. This is the value that tells us the partial pressure of oxygen at which red blood cells are 50% saturated with oxygen. Okay. So a decrease in the pH shifts the curve to the right. Decrease will shift it to the right, but the increase in pH will lead to more affinity. Okay. So it will shift it to the left. Okay. Yes. Hello, Tileshwar. We are discussing Unit 1 questions over here from CSIR exam. Given below are the various, now this is part C question. Again, this is a combined question with Unit 13. So Unit 1, Unit 13 has combined questions. From Shift 1 only this question is there. CNBR, cyanogen bromide, trypsin, caspase, chymotrypsin. So out of that, what will be the different substrates? They are given different substrates. Which one will cleave what? Which of the following option represents the correct combination of items? Okay. So here you have different combinations they have given. So we know that cyanogen bromide, it will be cleaving beside the methionine, right? So this will be the first choice. The C terminal of methionine, cyanogen bromide will cleave. Trypsin, we know that trypsin and chymotrypsin, they are proteolytic enzymes. So chymotrypsin is going to cleave beside the C terminal of hydrophobic residues. So here you have phenylalanine, hydrophobic aromatic amino acid residues, that is phenylalanine, tyrosine, and tryptophan. So chymotrypsin is going to cleave at the C terminal residue of phenylalanine. Okay, at the C terminal residue of phenylalanine. Then trypsin is going to cleave arginine and lysine, C terminal residue. So again, trypsin is going to cleave over here or cut over here. And caspases, yes, they are cysteine proteases. They require this aspartate. Beside that, they will cut. So simple logic you have to apply, and this is also a theoretical question. You can just check this list from Leninger book. So according to the list, CNBR cleaves at C terminal, trypsin cleaves C terminal of lysine arginine, chymotrypsin cleaves C terminal of phenylalanine, tryptophan, and tyrosine, and caspases are cysteine proteases which cleave C terminal residue to aspartic acid residues. So that's why this is the answer. So Tileshwar asks, is score 121 a good score to qualify in shift 1? I expect so, Tileshwar. I do expect you to clear with 121 score. Okay, because we are not expecting beyond 60% cutoff, right? So 121 is actually a good score to qualify. Now let's see, because 60%, 120 is 60%. And at Biotecnika, we are not expecting it to go beyond 56%. But anyways, they give in percentile, so we'll have to wait for it, right? Yes, if anyone wants to prepare further, so just remember, mirror on the wall, I'll always get up after I fall. Whether I run, walk, or have to crawl, I'll set my goals and achieve them all. You have to always be overcoming your fears and work towards your future, right? Shaurya batch is starting tomorrow. If anyone wants to see yourself working at an eminent research institute, then do hurry up for the enrollment, because we have very few seats left. You'll be getting a video pen drive for all the backup of classes. Okay, just in case you're not clearing this exam, then the next exam you can definitely take the help. It's starting tomorrow. You don't want to miss any classes. You want to attend right from the beginning. You can contact us. Yes, Tileshwar, OBC category means definitely you will clear. So there is no doubt on that. Okay, because I was talking about the unreserved cutoff. 60, 56, we are talking about unreserved. Okay, shift 2 part C questions. Let's discuss. Two experiments were performed on a peptide sample X. In experiment 1, treatment of X was done with dithiotretol, which is DTT. Now, what does dithiotretol do? It's a reducing agent. It will break the disulfide linkages. It will convert them into SH groups. Okay. And we know that proteins, they are bonded by disulfide linkages. So after that, the disulfide linkages are broken. They will become opened up. The SH groups will become opened up, right? Or else, if any protein molecules, they are having some subunits, and those subunits are joined by disulfide linkages. After you treat your protein with DTT, you can expect the subunits to separate. So two subunits will separate, and that's exactly what happened to this peptide, this entire protein sample X, where upon treatment with DTT, and you blocked the free sulfhydryl group, because if you block this opened up sulfhydryl group, then they cannot join back again. So they will stay separate as individual polypeptide. And that's what you got from this protein X. If you separated, you got two polypeptide chains, right? Now in experiment 2, it is a separate experiment. This is the result of experiment 1. That is the confusion that may appear. Now in separate experiment, X was treated with chymotrypsin, a protease that cleaves the carboxy terminal of aromatic residues, right? That is, we already saw. So amino acid composition of 5 peptides are obtained from this experiment, the ones which are shown over here. So you got some fragments. After chymotrypsin treatment, you got some fragments. They haven't given you the exact sequence of the fragment, but they have given you some, the composition of, in that particular fragment, which amino acids were there, right? So based on the above results, you have to find out, in here, in this entire protein, totally you had 4 cysteines, right? Not 4, 5 cysteines were there. So they had asked that how the cysteines are linked based on these two separate experiments. Okay, again I'm telling you, the experiment 2, it was only treated to the intact protein. Chymotrypsin treatment was done to intact protein, not separately. Okay, so you have to remember some connections might be there. Now, how do we solve this question? Let's have a look. Right? So, yes, answer was option 2. As I mentioned, DTT, what it will do, it will open up the disulfide linkages. And in second experiment, intact protein is treated. So, it will cleave the peptide bonds at C terminal of phenylalanine, tyrosine, and tryptophan. So, if you consider the treatment of the two proteins, the two fragments that you got, right? And you take all these residues, that is phenylalanine, tyrosine, and tryptophan, it will cleave at the C terminal. Always we write protein from N to C. So phenylalanine, it has this bonds this side, this side. It will cleave the C terminal bond, the one which is this side. So where all it will cut, just select all these residues in all the two fragments. So phenylalanine, here it will cut, tyrosine, here it will cut, tryptophan, here it will cut, again tryptophan, here it will cut, and phenylalanine, here it will cut. Now totally how many fragments you're getting? 1, 2, 3, 4, 5, 6, 7. 7 fragments you're getting A to G. Okay. But in that experiment result, if you see how many fragments they got after chymotrypsin treatment, they got 5. What does this mean? That 2 of them might be connected, right? 4 cysteines, 5 alanines. They have dissolution of the first subunit, alanine, phenylalanine. Now this looks the same composition as fragment 1, isn't it? Now let's check. So basically first composition will be of fragment A. Then let's check second composition. Aspargine, 2 cysteines, 1 methionine and 1 tyrosine. Now we do have cysteine, methionine, tyrosine, and in another one D fragment we have cysteine and aspargine. So that completes our composition of second fragment. That is 2 cysteines, cysteine A3. A means in A polypeptide chain third cysteine, and in cysteine and in polypeptide chain a ninth residue. So that means what? These two cysteines must be linked together, which was broken in the previous experiment with DTT. That's why you got them separated. Okay. Not separated by like DTT doesn't break backbone, but at least they were joined together, which might have got broken off. Okay. But here it did not get broken. And that's why you got this fragment and this fragment together as one fragment because they were linked with disulfide linkage. Right. So second composition is a mixture of both fragment B and D. Thus we can say cysteine A3 and cysteine A9 are linked together. So that's one of your disulfide linkage. Now, third composition you see cysteine, glycine, and lysine. So that is your fragment G. Yes, so over here you can see glycine, lysine, and cysteine. This is your fragment 3. Okay, fine. Fourth composition, if you see again, 2 cysteines are there. You have one leucine, 2 tryptophan, and valine. Now, if you see here, you have leucine and tryptophan over here. And here another tryptophan is there. Valine is also there, and 2 cysteines are there. That means what can you suggest? That these 2 cysteines are linked together. That is why in the first experiment, when you cleaved with DTT, you got separate fragments. That is polypeptide chain A and polypeptide chain B. But here, since these two are joined together, you didn't treat it with DTT in second experiment. So this and this you got as one single fragment. That is fragment 4. And fifth fragment, yes, the last one, which is isoleucine, phenylalanine, and valine. That's what your answer. A3 to A9 and B2 to A6. That's why option 2 is the correct answer. I hope you all are following. Now, another part C question in shift 2 was from Ramachandran plot. It graphically shows combination of torsional angles phi and psi of amino acid residues contained in a peptide. We know that there are some torsional angles. So, examination of the plot shows that only certain regions of conformational space is permissible. Other combinations are not possible. So, why are all the theoretical combinations not possible? We can see only few allowed angles in the Ramachandran plot for secondary structure. Why any other angle is not possible? So one option is two atoms cannot occupy same space. Geometry of peptide bond that links two residues restricts phi psi. Beta sheet and alpha helices, that is secondary structures, determine region of conformational space, or tertiary fold of polypeptide restricts conformational space. Now, if you know about Ramachandran plot, yes, option is answer key is option 1. So this is the peptide plane. Okay, this is one peptide plane, this is one peptide plane. You should know that in Ramachandran plot, the peptide bond is a rigid planar configuration. And the phi psi values are actually single bonds which can rotate freely irrespective of the peptide plane. That is why option 2 will become wrong, because it is mentioning that the geometry of the peptide bond decides the phi psi value, and that's why theoretical possibilities are not possible for phi psi. That's wrong. And theoretically, phi psi can have any value, but not all combinations are possible. Because if you think, see, this is a non bonding atom and this is another non bonding atom. Now, just imagine if this angle is rotating. So, what will happen? This will come closer. So, if this comes closer, there will be a steric hindrance. I hope you understand when some bonded atoms are there and these are their covalent radius, but this is their van der Waals radius. If they are too close to each other, then their van der Waals radius will allow, it will lead to repulsion. They cannot be present. So basically, not all combinations are possible in reality. Simple logic is there will be physical clash of atoms in 3D space. So atoms take up some space and two atoms cannot occupy same space. That is why all angle rotation of phi psi is not possible, and it can take only certain phi psi values where it will form certain secondary structures. Okay, and Ramachandran plot, if you plot your torsional angle, it will tell you what secondary structure it will contain, it may contain, and not the other way around. Okay, in option 3 it is saying that beta sheet and alpha helix can restricts the phi psi, but no, by looking at the phi psi only you can tell what secondary structures it will take. And in fact, if you have a possible value of phi psi, then only a possibility is there for obtaining a secondary structure. Okay, and tertiary structures are defined by the phi psi. Again, it's the same logic. Since you can say the secondary structures will decide how what type of tertiary structure will form. But option 4 is saying that the conformation of the protein restricts phi psi. Again, that is not correct. Okay, so correct option is option 1. With simple logic, two atoms cannot be at the same place. Okay, next question in part C of shift 2. This was regarding vitamins and some one statement from enzyme. Coenzyme B12 is an organometallic compound. Obviously, yes. Pyridoxal phosphate, yes, it is derived from PLP. It is again derived from vitamin, and it is used for amino transferases. Even this is correct. Affinity of biotin for avidin, yes, this is a very excellent choice for affinity chromatography, and we use it for many biological experiments. So it is the one with highest binding affinity. This is also correct. An enzyme catalyzes biochemical reaction. It acts as a biocatalyst by lowering the energy of the transition state. So we know that when molecules they have to go to a transition state, they need to be stable over there. Then only they can convert into the product, a particular substrate. So that energy which is required to go to the transition state is called as activation energy. Enzymes make activation energy lowered. So basically the energy required to get transition state is lowered, and that's how more substrates get converted into product. So it increases the rate of reaction. So even this is a correct statement. All statements are correct. Okay, A, B, C, D, all statements are correct. That is why the correct answer is option 1. Okay, so yes, when coenzyme was identified as organometallic, basically it has some metal carbon bonds. That's why it is organometallic. Pyridoxine, pyridoxal, pyridoxamine all act as vitamins. They are from B6 and are transformed to PLP, which is cofactor for amino transferases and amino acid decarboxylases also. Right? Yes, very good, Antara. All of them are correct answer. In biochemical work, biotin-avidin pair formation is widely used as anchoring platform, and their binding constants are very high, as much as 10 to the power 14 to 10 to the power 15, which is extremely high affinity. Okay, so it is in several orders higher than other type of non-covalent pair like antigen antibody, sugar lectin, enzyme inhibitor, all that. Heparin interaction comes a little bit closer to the affinity, but still avidin biotin has maximum binding affinity. And as I already mentioned, energy required to reach transition state, enzymes lower that affinity. Yeah, this is shift 2. Everything was discussed, Antara. We are almost done with everything. We are just doing the last part C, few part C questions from shift 2. Shift 1 part C I've already discussed. You can check the recording later if it is available. Okay. So pK of the ionizable groups in the tripeptide. This is the next question. Shown below, they are indicated in the structure. Right. So this is a tripeptide. Yes. This is your one amino acid. This is your another amino acid. And this is your another amino acid. So for always calculation, you have to find out the PI. For calculation of PI, we always have to select the alpha, that is the terminal amino group, terminal carboxyl group, and whichever side chains are ionizable. So in this case, lysine side chain is ionizable. We can clearly see there is a lysine over here. Phenylalanine is not ionizable, which is having this phenyl group. Even CH3 is not ionizable. Yes, yes, that's right, Antara. Very good. So we have to find out the isoelectric point. Basically, isoelectric point will be where the net charge of the peptide is 0. So what we will do is here we have 3 functional groups and 3 pK points, which means total 4 forms we will get. So if you consider the 4 forms of all of them, let's see what will be the answer coming to. Yes, the answer is option 1. So since the peptide has 3 pK points, it will have 4 forms. So one is the fully protonated form, where NH3 plus alpha group is protonated, R group is protonated, alpha carboxyl group is also protonated. So what are the charges on them? Plus 1, 0. So total charge is plus 2. Then comes the form 1 after alpha carboxyl group has dissociated. So from COH group, it will become CO minus. So then the charge from 0, it will become minus 1. So total charge then will become plus 1. Form 2 after dissociation of alpha amino group at pK2. So now what was plus 1 over here in the alpha amino group, now it will become 0 because it has converted to NH2. So total charge is 0. Then form 3 is fully deprotonated form after dissociation of R amino group at pKr. So pKr means this group also has dissociated. So 0, 0 and minus 1, total charge is minus 1. So we are seeing that the net charge, we know the PI point, it is the net charge where it is 0. We have to take the pK points before and above it. So what caused this 0 charge? That is pK2 and pKr. Because if you see, when did you get 0 charge? After pK2. Till what time it was 0 charge? Before pKr. Because after pKr it became minus 1. Before pK2 it was plus 1. So we have to take these two pK values. In between that only your PI will lie, where net charge will be 0. So you have to take an average of that. 9.8 plus 10.5 divided by 2, 10.15. Option 1 will be the correct answer. Okay. Yes, Antara, you're right. Very good. Next question in part C shift 2 was enzyme kinetics. You have to calculate the fold difference between the velocity. Initial velocity you have to find out. At substrate is km and at substrate is 1000 km. So substrate, km, they haven't given the km value. So you have to assume something. And basically you have to find out the difference in the velocities. So what you will do? Separately, you have to substitute in Michaelis Menten equation, right? So here also answer was option 1. We know Michaelis Menten equation is V0 is equal to Vmax into S divided by Km plus S. Now they have given substrate concentration. So for first case, we will consider substrate is equal to Km. Okay. And in second case, we will assume substrate is equal to 1000 Km. And then rest put the values as it is. So when substrate is equal to Km, then V0 what it will be? Just put in the equation, consider this as V01. So Vmax as it is, we are putting, instead of substrate, we are putting Km. So Km is as it is, and instead of substrate, we are putting Km. Just calculate this. Km plus Km will become 2 Km. Vmax into Km will be there. Kms will get cancelled because it is multiplication. So it will get cancelled. Basically, your V01 is Vmax by 2. Then in the second case, or you can also say V01 is 0.5 Vmax, right? Then second case, we will consider S is equal to 1000 km. Then what will be your V0? So here, substrate, instead of substrate, you will put 1000 km. Similarly, here, instead of substrate, you will put 1000 km, right? Now just calculate. So this is 1 km, don't forget that. So 1 km plus 1000 km is what? 1001 km, right? So again, km will get cancelled because both are in numerator and in multiplication. So basically you get Vmax into 1000 divided by 1001. So 1000 by 1001 you will get 0.99. That is Vmax 0.99, or you can say 0.99 Vmax. So you have got your V01 and V02. You have to find out the difference. All you have to do is V02 divided by V01, that is 0.99 Vmax divided by 0.5 Vmax. Vmax gets cancelled. 0.99 by 0.5 is 1.98. First option is the correct answer. Okay. And then one more question was there for purine and pyrimidine nucleotide. They serve as monomeric units of the nucleic acid polymers DNA and RNA. They have said biosynthesis of both purine and pyrimidine nucleotide begin with ribose 5-phosphate, and purine and pyrimidine rings are built on it. We know that we have a ribose sugar, on that you have a pyrimidine ring or purine ring, whatever it's there. So in purines, what happens? You have the ribose sugar, and then one by one the molecules are built upon on it. Okay. So for purines, this is applicable, but for pyrimidines, it is not applicable, because for pyrimidine synthesis, the ribose sugar is separately made and the pyrimidine skeleton is separately made. Then they are joined together. Okay, then they are joined together. That is why this is not correct. The first purine nucleotide synthesized is inosine. Even this is correct. First pyrimidine synthesized by de novo pathway. De novo is where you make the nucleotides from scratch. It is orotidylic or orotidine monophosphate. Even that is correct. And thiamidylate or TMP synthesized as deoxy TMP. Even this is correct, because deoxy UMP, that is simply DUMP, gets converted into DTMP. Then DTMP will get converted into DTTP. That's the sequence. So even this is correct. Okay, and the enzyme is also right. You have to select incorrect statement. So only incorrect statement is option 1. That is, statement 1 is incorrect. Okay. So as I mentioned, the explanation, how they are built. Yes, they are built. Pyrimidine is built first as ororate. Later it is attached to ribose phosphate, and then it is converted into other nucleotides. So option 1 is wrong. First intermediate with a complete purine ring is inocetate. As you can see, this is purine synthesis. From ribose pyrophosphate, you make PRPP, then 1,1 addition and all. It will lead to the formation of inosine monophosphate, which can convert into either AMP or GMP. And for the pyrimidine ring, as I mentioned, the first ring completion, that is in the form of ororate, and later it will be converted, oxidized to the pyrimidine derivative ororate, a reaction in which NAD is the acceptor. And the immediate precursor of thiamidylate is DUMP. So you can see here, UMP converted into DUMP, DUMP converted into DTMP by thiamidylate synthase, and DTMP to DP, and DTDP to DTTP. So that's why the last statement is also right. The last question of shift 2 from unit 1, it was a combined question with, you can say unit 2 or unit 6, you can say, okay, and even unit 3, although it doesn't help in replication. So basically cyanide, how it is toxic. Okay, so if anyone has done a decent preparation, they will know that it blocks the complex 4, and because it blocks complex 4 in electron transport chain, it will inhibit electron transport chain, and it won't be coupled to oxidative phosphorylation. So ATP synthesis will not take place, right? So A and you have to select with all correct statements. A and B is the right statement, because it doesn't have anything to do with DNA replication, and also it doesn't block TIM-TOM channels. Okay, so as you can see over here, yeah, so sorry, it will be option 1, because sorry, it will be option 1, because yes, it will block the mitochondrial DNA replication. So you can see what is it doing. Cyanide's main effect is that it inhibits oxidative phosphorylation. So B is correct, a process where oxygen is utilized for the production. Actually it is option 2. Okay, I should write option 2. Yeah, so energy sources in the form of ATP. You can see that it uncouples mitochondrial oxidative phosphorylation. See, cyanide treatment, what it is doing? It is inactivating the complex 4. So because of complex 4, you can see there is an uncoupling of the mitochondrial oxidative phosphorylation. So there is no cellular respiration. So A and B is correct. It does so by reversibly binding to the ferric ions of the coenzyme C oxidase and blocks electron transport. Right? So that's all from my end. Again, I want to remind you that you can join the Telegram group where this question paper solved question paper from Biotecnika will be posted. The link will be given in your comment section. You can join our Telegram group, and Shaurya batch is starting tomorrow. The first class will be at 7 o'clock. If you want to attend, then you have to enroll and inquire now, because the seats are getting filled up very soon, right? Registrations are open. You will get live classes and doubt solving, printed hard copy materials along with free printout. I hope that was helpful to you all. Thank you for attending the session. Tomorrow, don't forget to log in again for Unit 2 question discussions of June 2021 CSIR exam. Thank you, everyone.